Okay, let's get started. It's my great pleasure to welcome Professor Andrea Young today from UC Santa Barbara. So Andrea is a real pioneer in the field of 2D exfoliable materials. For the better part of the last 20 years, he's been contributing seminal work one after another, particularly in the field of graphene. Andrea got his PhD from Columbia University, working with Professor Phil Kim when he was still there. He started working with graphene on silicon dioxide and managed to do beautiful experiments like demonstrating Klein tunneling in graphene using those devices. But later on in his PhD, he realized that graphene on hexagonal boron nitride, which we all take for granted these days, was really the way forward for very clean devices. And using graphene on HBN, Andrea managed to do some beautiful experiments on fractional quantum Hall effects in graphene during his PhD. He was then awarded a Topological fellowship at MIT, where he continued to work on graphene. In particular, he started to think about moire physics between HBN and graphene, and did some seminal works on measuring Hofstadter butterfly spectra in graphene, which was never done before. He also contributed works demonstrating quantum spin Hall effects in graphene. He then had a short visiting appointment at the Weizmann Institute, where he worked with Ellie Zeldov to get trained on developing squid magnetometry at the micro and nano scale. And now bringing all these different tools to bear in his lab at Santa Barbara over the past 10 years or so, he's continued to churn out seminal work one after another in graphene, thinking about topological phases in graphene heterostructures, looking at twisted graphene and trying to understand strong correlation physics, ranging from correlated insulating phases to superconductivity. And I think we'll hear a summary of all the exciting works that Andrea's been doing today. So for all these contributions, Andrea's been recognized in a variety of ways. Too many to list now, but highlights include the Sloan Fellowship, Packard Fellowship, Macmillan Award, and more recently, the New Horizons Prize. So let's give Andrea a welcome.
Thanks, everybody. Let me know if this is loud enough. So yeah, thanks, David, for that kind introduction. So today I want to try to focus on one sort of unifying theme that's been a driver of the physics that we try to do in my group. Not the only thing, but certainly sort of the central idea, which is the idea of trying to use topological aspects of condensed matter systems to realize electronic devices. And the reason that I want to frame this talk this way is that there is, of course, the seminal discovery of integer quantum Hall effects was just an electronic phenomena. You measure the resistance, and it does something that you cannot get a normal resistor to do. And the basic animating idea of this talk is whether, powered by advances in two-dimensional materials, you can try to make new types of things out of topology that you couldn't make some other way. And so I'll show you a few examples of that. So to start, let me come back to the basics and ask if anybody, I think I may have even shown this slide the last time I gave a colloquium at Caltech, so maybe some of you will remember, probably not though. So does anybody know what this is? It's the inside of a chip resistor. Does anybody know what that little weird shape in it is? You know. What is it? It's adjusting the resistor, right? So like if you want to buy 10 mega ohm resistor or 10 ohm resistor, but it's 10.000, right? You can't manufacture that. What these are gold. So these thick things are gold, and these sort of bronze shaped colored things are a thin film. That's where the resistance actually is. And then every single one of these precision resistors that you buy, you have to go with a laser, and there's a machine that does it, but it's going to measure the resistance, and it's going to basically sputter away a little piece of that film until the resistance is 10.000 ohms, right? And about the best you can do is like 3 or 4 digits of precision by doing that, okay? And And it comes from the fact that, materials are not perfect. It's hard to make a perfect material, right? And every system is never a perfect material. So, you kind of got to do some engineering to work around it. And that's fine. You can buy this for, $10 or $20. That's good, right? But okay, there's another example of how to get a precise resistance, right? This is not a way to make a standard of resistance. It's not the way we do make the standard of resistance. Rather, we use a completely different concept, which is to, rather than encode, rather than try to get a precise resistance by using, an imperfect material, which has an approximately known resistance, but not precisely, that then you have to shim basically and do some engineering, you can use topology. And use topology is a little bit of a strong word. What was discovered was that there is an effect, the integer quantum Hall effect, where the resistance of a material, specifically the Hall resistance, is quantized in units of fundamental constants. And this is because the resistance of this material depends only on the topology of the band structure, basically some sort of topological invariant of the band structure. And this really works well in experiment. This is an experimental discovery, okay, where you can see that as a function of gate voltage or magnetic field in any two-dimensional electron system that's reasonably pure, you find that the resistance is quantized to many digits of accuracy to precisely these fundamental constants of nature. Okay, so this is a much better way from that point of view to make a really precise resistor. So the question is, if you wanted to make a precise resistor like this out of nichrome, it's really hard. It's even more expensive than running, a dilution fridge to measure this resistance. So it'd be very difficult to do. Okay, so the basic and the way we understand this is that there's a topological invariant called the Chern number, which is a property of bands in any sort of periodic system or even an aperiodic system to some degree. And you can relate the Hall conductance precisely to this Chern number. And because this Chern number is some topological invariant, it can only be an integer number. And this turns out to be a property essentially of all non-interacting insulators. If you break time reversal symmetry, they all are going to have a quantized Chern number. That Chern number can be non-zero, and therefore you can get some Hall conductance that is quantized in these units. Physically, and I'll just introduce it now because it's going to be important later in the talk, this Chern number, which is a property of the bulk bands, the way this actually manifests in an experiment is because each of those quantized Chern numbers from a bulk band generates an edge state at the edge of the sample, which is chiral. So the physical picture here is of a two-dimensional electron system seen from the top. These yellow bars are supposed to be the electrical contacts, and the physics of, let's say, a Chern 2 insulator, like let's say a fully filled Landau level. Landau levels are sort of the paradigmatic example of Chern bands, the first ones where this was all studied. At the edge, you'll have two single quantized conductance modes, which can only carry current in one direction because they're single quantum modes. They carry exactly E squared over H conductance. And because they are chiral, meaning they only travel in one direction on one side of the sample and the opposite direction on the other side of the sample, there's no backscattering, there's no way for current to relax, and this conductance stays perfectly quantized as long as the sample is made reasonably large. Okay, and every time you change the Chern number of the bulk, this property of the bands, by filling another band, which you might do by tuning a gate voltage in a field effect transistor, for example, you will increase the Hall conductivity by 1, which just increases the number of edge states by 1. Okay, and you can sort of work out why this would give you the signatures of the quantum Hall effect. I'll leave it sort of as a textbook, it's a textbook exercise to understand this relationship and why it gives you the physics of the quantum Hall effect that's observed. Okay, so in this talk, I basically want to talk about 2, maybe 3 different properties of edge states that can happen in these types of systems, which are new things that we've been able to observe thanks to some developments in graphene heterostructures and so on. So one of them, the first part of the talk, I will talk about the fact that these chiral edge states actually have a magnetization associated with them, and that under certain circumstances, you can use that magnetization to make one impossible electronic device, which is a magnet whose direction you can reverse by applying merely an electric field with no current flow. Okay, so you can tune an electric field and have a magnet switch up and down by manipulating the magnetization, the equilibrium magnetization of these chiral edge states. And in the second, I'll talk about something a little bit more intricate, which is a related effect called the fractional quantum Hall effect, where the edge states take on a very unusual property where they have fractionalized charge, and you can use these to actually build another impossible electronic device, which is a direct current voltage basically voltage transformer, something where you can put in one voltage and get out a voltage that's higher, but operating entirely at DC, basically by transmuting fractional charges into integer charges. So I'll walk you through those things. And then if there's some time, I'll show you new measurements of the anion phase in fractional quantum Hall states in graphene. Okay, so to just introduce, what it is we do, David mentioned this a little bit, and I think there's plenty of people in the audience who are familiar with the basic practice here. We study two-dimensional layered materials. It remains to this day, again, as David sadly reminded me, nearly 20 years after the discovery of graphene, we still basically make it the same way because it's the best way to make it, which is to start from clean bulk graphite and essentially peel it with Scotch tape. You can do it in more sophisticated ways, but it makes absolutely no difference. You get sort of the same result at the end, which is reasonably large sized, tens of microns or a couple hundred micron size flakes of graphene. This is what a monolayer looks like. This is what multi-layers look like. And you can basically spread these on a substrate and identify them, and that's your two-dimensional electron system that you're going to work with. Now, the important thing is that you are not confined to just studying a piece of graphene. You can turn these into heterostructures, and you do that by combining them with insulating or semiconducting or other metallic two-dimensional electron systems. And the most important of these is something called hexagonal boron nitride. It has exactly the same crystal structure as graphene, but rather than having two carbon atoms on the vertices of these hexagons, you have a boron and a nitrogen atom on every other vertex. So this is an ionic crystal, and it has a very large band gap in the deep UV, whereas graphene is a semi-metal, let's talk about. So you can use this as a substrate and as something that you use essentially to scaffold these heterostructures, separate layers, or use it as a dielectric so that you can apply gate voltages. The way you can assemble these, this is sort of one of the more recent ways of doing this, but there have been many ways over the years since we first started this back during my PhD, is you can start with some sort of sticky film, like a polymer, but you can also use a metal or any number of things, and basically bring it into contact with a 2D crystal, even a single atomic layer. And then you can lift that off the substrate, and now you have it on this platform, and then you can use that layer to pick up more layers. And you can basically build a complicated heterostructure, one atom thick layer at a time, basically by hand. And for many materials, all of the work I'll show you, this is done in air, under sort of normal laboratory conditions. Okay, what it actually looks like, this is a view through that polymer. As you spread it on the surface, you see these sort of Newton rings. As you squeeze it, this is a piece of boron nitride. And then as you retract that film, you'll see it pop off, I think, in the next frame. Boom, there it's gone. Okay, so now it's on that basically sticky substrate, and now you can pick up new heterostructures. So you can do this over and over again. So here's a heterostructure that we made for reasons I won't get into with a lot of layers. And you can see you can use a graphite, and then a boron nitride, and then a monolayer of graphene, and then another boron nitride, and a bilayer, and a boron nitride, and a monolayer, and a boron nitride, and so on and so forth, right? And you can do all of this, again, like pretty easily. You can train an undergrad to do this in, a couple of weeks. Certainly, a UCSB undergrad, a Caltech undergrad, probably do it in a couple of days. And the sort of remarkable thing is that, through a succession of improvements to this process, you can now make these two-dimensional electron systems, even though you're doing this basically with sticky tape and air, has the same type of quality as you get in, a $1 million molecular beam epitaxy system with 3-5 semiconductors, which is extremely well controlled and well studied system. But then you also get some more flexibility. So in particular, because you can build in electrostatic gates very easily, take a piece of graphite, pour a piece of boron nitride and a piece of graphene. The graphite is now one plate of a capacitor, the graphene is another, and you can apply very large voltages because you have this 5 electron volt insulator in between. You have a huge range of number of carriers. You can change the density inside this by a tremendous range. Okay, so you can access all kinds of physics just as a function of density. This is always a property of the experiments. But then you can also play with other types of structures, including structures that are not necessarily stable structures that would be hard to grow. So good examples, one of which I'll touch on in the talk today, one of which I will talk about tomorrow, is either rotational misalignments between layers, things that maybe would be difficult to grow, but can change the electronic structure in important ways that give you new physics, or stabilizing things like rhombohedral graphite, which is different from Bernal graphite. Bernal graphite being the graphite that you know, it's AB, AB, AB. Rhombohedral is ABC, ABC, ABC. It turns out it's kind of not that hard to stabilize rhombohedral layers too. And all of these have slightly different electronic structures and can give you radically different types of correlated electron physics or even single particle electron physics. Okay, so let me move to part one. That's the sort of basic experimental, that's the setup of how we make these types of samples, right? And we have a lot of control over what we do. So the first thing I want to talk about is basically the role of, the interplay between topological edge states and orbital magnetism. Okay, so at first blush, there's a lot of work to do, because if you think about monolayer graphene and its electronic structure, it's a very unlikely magnet. So monolayer graphene, it's just a single layer of carbon atoms. It's the elementary building block of all of the graphene, all of the graphite type materials that you're going to study. And its electronic structure famously is described by these massless Dirac electrons, where you have 2 flavors per spin, so 4 flavors total. One of each of these 2 flavors is located at the corners of the Brillouin zone. Okay, and if you think about, is this a likely candidate to be a magnet? The answer is not really, because this massless Dirac dispersion basically means there's almost nothing that's going to give you the usual ingredients of magnetism are not there, and the fact that it's made of carbon doesn't help either. So specifically, right, the first problem is there's very little anisotropy. Carbon has very weak spin-orbit coupling, right? And usually, if you want to have magnetic order, it's easier if you have some type of like Ising anisotropy. Then you'll get more. It's easier to order, right? Most ferromagnets that we have are easy axis. But if there's no spin-orbit coupling, you kind of almost don't expect any order at all in a 2D system. Okay, so the lack of spin-orbit coupling is a problem, right? The other problem is that when we think just heuristically about like what makes a ferromagnet, you have some interplay, let's say in a Stoner picture, between the fact that electrons have a finite bandwidth, and it costs kinetic energy to have them occupy the same spin. So you need interactions to be strong compared to kinetic energy, right? And in graphene, you have extremely low, very large bandwidth. You have an 8 electron volt bandwidth and essentially very low density of states. In fact, it's vanishing as you are when you're near charge neutrality, when you're in this massless Dirac dispersion regime, which is where we do all of our experiments. Okay, so low density of states, no spin orbit coupling. What are you going to do about it? Okay, so the answer to the question of spin orbit coupling is actually turns out to be sort of simple, which is don't use the spins at all. Right? The fact that you have these other flavors, these valleys, turns out to be very important, because if you can gap out these Dirac fermions, so if you can introduce some sort of perturbation which will gap them out, you get a lot of Berry curvature in that band. It's said that like Dirac cones have incipient Berry curvature. Almost anything you do to them will give you a lot of Berry curvature. And if you get a lot of Berry curvature, you get a large orbital moment. Now that orbital moment will be equal and opposite in the 2 valleys, but at least it's a degree of freedom which is very much Ising-like. This is obviously very anisotropic. This is actually a physical, you can think about it as a current that's flowing in the plane. In a monolayer of graphene, this current flows in the plane, but it does not flow out of the plane, right? This is an orbital current. Okay, so that's our degree of freedom that's going to be important, is that if you can gap out these Dirac cones, you're going to get a large orbital moment. Okay, then you need to make interactions strong. You need to somehow reduce the bandwidth, or at any rate increase the density of states. Okay, and it turns out the way to do that is generically interlayer coupling. So this massless Dirac dispersion is immediately spoiled as soon as you have 2 layers of graphene. And it turns out not to matter at all how you put that second layer, you're always going to find magnetism somewhere. That's something that we've learned in the last couple of years. So if you add a couple of layers in a rhombohedral structure, for example, this is just a pretty common allotrope of graphene, you find that the band structure is no longer just Dirac cones. This is energy versus momentum, but actually it has this sort of complicated structure, and it has these Van Hoff singularities. These are points in the band structure where the density of states diverges. Okay, and when it becomes very large, if you tune your chemical potential through these, so you try to occupy these states where you have many states to choose from, they will generically become magnetic. And in fact, in almost every type of graphene at this point, you can find a regime of parameter space where you're near one of these Van Hoff singularities, which are just a generic feature of interlayer coupling and the C3 symmetry of this lattice. You can find regimes where you have some kind of magnetic state. So here's rhombohedral graphene. You see, you sweep a magnetic field and just measure the Hall resistance, and you see that there's hysteretic behavior that's associated with polarization into one or the other valley and the formation of a spontaneous orbital moment. The system I'll tell you about today in the first part of the talk is actually, a different way to get large density of states, right? Which is to take two graphene monolayers and twist them on top of each other. It's another way to introduce interlayer coupling, right? Which generates a large density of states if you choose the angle just right. So at 1.1 degrees, you'll get a large density of states, and then that large density of states is sort of the right situation for interlayer coupling. What's important, though, about these moire systems is that they also introduce a superlattice. Okay, and that superlattice gives you something commensurate, and you can now think about band structure not only at the scale of the whole graphene Brillouin zone and the lattice of the graphene, which is angstrom scale, but rather now something that's more like 10 nanometer scale. This is important because if you want to get incompressible insulators in a solid state system, you need to be at some commensurate filling of the lattice. And commensurate filling of the lattice in a graphene crystal means zero charge density. But once you have the superlattice, you have a whole new superlattice band structure, and you can imagine insulators that happen even at finite carrier density relative to charge neutrality. That's going to be a very important thing. Okay, so this system was, got very famous in 2018 because there was discovery of correlated insulators, which means there's a flat band at partial filling, and then superconductivity near these correlated insulators. I'm sure you've heard many talks about this type of system in the last few years. Stefan's done some important work here about in these sort of moire systems. Among others, the important thing for this talk is that, just like in rhombohedral multi-layer graphene, there's generically magnetism. It's going to show up in these systems here and there. Okay, so the first experiment that was important to talk about for this talk is that if you tune things just right, and I'll sort of elide some of the details, but you need to have twisted bilayer graphene that has the right angle, and you need that moreover to be aligned to the hexagonal boron nitride, which actually gaps out these Dirac points. And there's sort of a conspiracy of small factors, which we chanced upon more or less at random, but have since sort of been able to understand and reproduce to some degree. If you look at resistivity here as a function of charge carrier density, so we have this twisted bilayer graphene, and we're tuning the charge carrier density. On the top axis is the number of electrons per superlattice unit cell. Okay, so if we go to 3 electrons per unit cell, what I want you to notice is that this orange curve, which is the Hall conductivity, is very large, gets very large, and the blue curve, which is the longitudinal conductivity, gets goes nearly to 0. Okay, and if you do a careful measurement right at 3 electrons per unit cell of the Hall conductivity or the longitudinal conductivity as a function of magnetic field, you find that indeed it's magnetic, but moreover, that Hall conductivity is quantized, and the longitudinal conductivity vanishes just like in the integer quantum Hall effect. Okay, but except instead of happening at high magnetic field because of Landau level physics, it happens at 0 magnetic field. Okay, and it turns out this is an example of a quantum anomalous Hall effect, okay, which is an idea that goes back to the 1980s. After the discovery of the integer quantum Hall effect, Duncan Haldane asked the question basically, do you need to have a magnetic field? Is that essential, right? You need to break time reversal symmetry. That was understood well, because if you don't have broken time reversal symmetry, then the Hall conductivity has to vanish. But he came up with a model where it's kind of a complicated model to understand how to do in an experiment, but basically said you don't really need a net magnetic field. And since then, it was the ideas were developed for trying to use just magnetic ordering in a material to break time reversal symmetry and get a quantized Hall effect. Now, in 2013, this effect was seen by introducing magnetism by basically sprinkling magnetic dopants inside a semiconductor that was appropriately designed. It worked. It was a very low temperature effect, and moreover, it became a very disordered system because you had to add these dopants, and it just messes up the rest of the crystal. It turns out that this system that we study, you can understand actually in a very simple way from just an intrinsic effect. You have these relatively flat bands that come from this high density of states. And if you just ask what is the lowest energy configuration of this system when you put 1 electron per unit cell, it turns out the system just prefers to occupy one of these bands. And these bands have a finite Chern number. It's something you can understand quite well theoretically. It comes from the same Barry curvature that generates these orbital moments, right? And it will just spontaneously magnetize. Okay. Now, this raises an interesting question because the nature of the magnetism in these systems in general is mostly orbital. It comes from the fact that the electronic wave functions have essentially equilibrium currents in the plane. The spin plays actually a relatively negligible role. So these are orbital magnets. Okay. And there's a theory for orbital magnetism, at least for non-interacting electrons, which is roughly applicable. You can think about this as, for the occupied states, what's the projection of the angular momentum operator if you think through the physics of the block wave functions, okay? And there's sort of, people usually talk about two contributions to this. There's some part that comes from wave packet self-rotation, and then there's a part that comes from center of mass motion, if you want to think about wave packets propagating in a solid. Okay, and the interesting thing about an intrinsic orbital quantum anomalous Hall state, which is what we have, is that this wave packet self-rotation, it comes from the bulk bands. But even if you're inside an energy gap, so if you're inside a quantum anomalous Hall state, you just have the edge state, that edge state itself has equilibrium currents, which constitute some amount of magnetization. So if you change the occupation of this edge state, actually that's a very large diameter current. So it's a pretty large effect. It's a pretty large orbital magnetization. The interesting, so one of the experiments we wanted to do was to sort of try to understand quantitatively, first of all, just is this indeed an orbital magnet? Okay, so to do that, I'll just talk about this very briefly. If you ask, like, what are the magnetization densities in these are very low density systems. They have something like, 1 electron per 1 Bohr magneton per electron, roughly. Maybe it's a few times that because of the orbital magnetization. And 1 electron, or 10 to the 12 electrons, or 10 to the 11 electrons per square centimeter. It's actually 1 electron per 10 nanometers, right, or 15 nanometers. It's a very small magnetization density if you want to compare that to like iron magnet that's on, neodymium magnet that's on your refrigerator. So you can try to say, well, what would it take to actually image this directly? And you can do the rough calculation and say, well, the fringe magnetic fields you're going to be able to see if you just try to look at it are 100 nanotesla, 10 nanotesla. They're really quite small. So to do this, it's part of what we built this, this type of instrument for. We use these nanosquids on tip. They're tiny little squids you can make on the tip of a quartz tube. They have, strong magnetic response. Actually, they work up to quite large magnetic fields because all of the dimensions are so small. Very recently, we've been able to improve these by another order of magnitude. So we now have magnetic field sensitivities in the picotesla per root Hertz regime, which is really very small fields. It makes it possible to detect a single spin inside your squid loop, in a few tens of milliseconds. And we can operate these at low temperatures. We can sort of navigate them to where the samples are. So one of the first experiments we did with this tool was to precisely measure this orbital moment. And you can see that, in fact, the orbital moment is, a few times larger than the spin moment. Every electron carries mostly an angular momentum that comes from its orbital magnetization, and a little bit, maybe 1 Bohr magneton from the spin, given that there's no spin-orbit coupling. Okay, so it looks like this is indeed an orbital magnet, and we've since seen this in many of these other graphite systems. They all have these orbital magnetic states. These orbital moments can be actually quite large, even few tens of Bohr magnetons. But the important thing for, the thing I want to sort of point out is that these are really fundamentally small magnetizations, right? Typically, if you ask in, let's say, a quantum anomalous Hall state, you have some magnetization of the edge state, but let's say you've made this by sprinkling magnetic dopants to make a semiconductor magnetic. That's a huge magnetic density that you've put in, and the edge state is a very small proportion of that. Here, the edge state magnetization, this equilibrium current that goes around the edge, and the bulk magnetization, they have the same origin. They come from the same bands. They're normally the same sort of order, okay? And it turns out that there's an interesting opportunity to see an interplay that between basically filling the edge state and filling these bulk moments that can give you sort of a new functionality. Okay, so to do this, we have to move to a slightly different system. It's another moire system. It's twisted graphene monolayer on bilayer. The reasons to do this were, totally practical. There's nothing intrinsically. It's just much easier to reproduce the same type of physics. What you can see is that as a function of both the electric field applied across the system and the charge carrier density, you have some, these spikes that are happening at odd and even filling, which is corresponding to partial filling of these energy bands. And in particular, if you look at 1 or 3 electrons per unit cell, you see that there are indeed quantized Hall effects that are happening, quantized anomalous Hall effects that are happening at those fillings. So it reproduces the physics, but there's actually one funny feature that occurs if you look at 3 electrons per unit cell. Again, it's random as far as, it's some detail question why this happens at 3 but not at 1. But when we first looked at this data, we thought, there's a cable loose, like why is this switching back and forth? What you're doing is you're varying the charge carrier density by an electric gate, and then you're varying the magnetic field and you're switching it back and forth, and just nothing seemed to stay at the same value. Okay, get trapped. So in fact, I thought I told my student that this was probably an experimental problem and we should ignore it, and luckily he didn't listen to me. It turns out that it's actually a very interesting effect. Okay, so if you do this very carefully, these are quantum anomalous Hall states. They have hysteretic behavior as a function of magnetic field. So the Hall conductance will switch sign because you're basically reversing the polarization of your valleys, which will reverse the Chern number, which will reverse the Hall as a function of magnetic field. That's all as it should be. But it turns out, so this is a little bit complicated to look at, but it's a 3D plot where on one axis, we're doing exactly that hysteresis loop. So in blue and green, you can see a hysteresis loop as a function of magnetic field. But you can actually achieve the exact same thing by tuning an electric field. They basically just trying to change the chemical potential in your 2D system. And you can switch back and forth between positive and negative quantized Hall conductance just as a function of an electric field. Okay, so what is going on? The basic conclusion here is that in a small magnetic field, which is where we operate this, your system prefers to be in the ground state. The ground state means that the magnetic moment of your whole system should be aligned with the magnetic field. Now, clearly, if you change the sign of the magnetic field, you're no longer in the ground state. And if you have some metastable, irreversible dynamics, you will, eventually relax to the ground state, which is now the opposite valley in this case. But it turns out there's 2 ways to change the sign of this term. One is that you can change the sign of the magnetic field, and the other is you can simply reach into your system and change the sign of the magnetic moment, right? There's no real analog of this for spin, or even for spin orbit coupled systems in semiconductors, because usually the G factor is simply a number, right? It's something that's sort of set at the UV scale if you want, and it's not something that you actually can manipulate. But in these systems, this magnetization actually has contributions from the bulk, and it also has contributions from the edge. And it so happens that the bulk contributions in this system have one sign, and the contribution from the edge, which is proportional to the Chern number and the size of that energy gap, has the opposite sign, which means that just by populating an edge state, you can go from having a positive magnetization in one valley to having a negative magnetization in that valley. So if you're at some field, you were in the ground state, and now all you did was populate a little bit of edge magnetic moment, and now you're no longer in the ground state. You're now in this favored state, and you'll get relaxation. Okay. So what this means, so just to illustrate this, right? You might start off in a system with, at some voltage on your capacitor where you populated the bulk, but you haven't populated the edge state, and you're in the ground state. The field is pointing out of the plane. And now you might tune the gate until you populate the edge state, but now you've reversed the sign of the magnetization. You're no longer in the ground state, and now you relax. You relax to the other valley. But now you switch the sign of the magnetic field, right? And now you're switched to the, so now you switch to the other valley, and then you can tune, sorry, and don't forget about the magnetic field. You switch to the other valley. This is the reversal that occurs when you jump to the other arm of the hysteresis loop. And then as you tune your gate, you now are again no longer in the favored state, and you do this over and over. And so it turns out you can do this over and over again. I call this the world's most expensive magnetic bit because we did it one time. It was a very long running experiment, but you can in fact, switch the magnetization, which you can read out through the Hall effect, just by switching an electric field in a capacitor, right? So it's actually something kind of difficult to do. You can try to switch magnetic moments. For example, the way magnetic memory works in MRAM is that you drive large currents, and these currents exert torques on magnetic moments. And this is actually a highly dissipative process. Here, you're putting a tiny amount of charge in probably like an attofarad capacitor, and it's enough to reverse like a macroscopic magnetization on like a several micron scale. Okay, so it's an extremely, for all intents and purposes, zero power switching of a magnetic moment. Okay, and it turns out this is a pretty generic effect. Since this experiment, you can find this. You can do it even without edge states. You can do it in all of these types of. It's really a property of orbital magnetism, which is that once your magnetism comes from the block bands, and your block bands have a lot of texture, this can be positive, it can be negative, and you can tune it, and you can see all kinds of switching phenomena like this. Okay, so that's the end of part one. Let me move on to the second part of the talk, which is focus on fractional quantum Hall physics. Okay, so let me start actually with just talking about these edge states themselves, right? So besides the fact that they have some equilibrium magnetization and quantized conductance, they are 1D systems, right? And we know a lot in condensed matter physics about the physics of 1D systems. Some people say we know everything about 1D systems. The most basic fact about 1D systems is that in the presence of interactions, they're quite different from 2 and 3 and higher dimensional electron systems. They're called Luttinger liquids, okay? And maybe a characteristic feature of Luttinger liquids is that the elementary excitations of electrons that interact in one dimension don't resemble the electron itself very closely. So this is something called the orthogonality catastrophe, and the basic idea is that at low energy, if you ask like what's the, this is a metallic type of state, but the low energy excitation actually has no overlap with the electron wave function. So if you try to put an electron into a 1D system at low energy, you cannot do so. Okay. Now at finite energy or at finite temperature, you can do so, right? And the degree to which you can do so is characterized by power laws, which are given by something called the Luttinger liquid parameter. Okay. So for example, the conductance of tunneling into a Luttinger liquid from a 3-dimensional electrode, let's say, is going to be characterized by some power law. And that power law is sort of a detailed property of the system. It depends on how strong the interactions are, maybe how thick the system is. So for example, in carbon nanotubes, a famous experiment from the 1990s, saw this type of power law behavior. It was evidence you had a 1D electron system. And they measured some number for this G, 2.6, but then it was 2.4 and other nanotubes of different sizes. And it's something that depends on the details, as it should. Like, that's the idea. It's just like, the effective mass. It's just a number that depends on the details. But turns out things are kind of different. There's an exception to this, okay, which is in the physics of the fractional quantum Hall effect. So fractional quantum Hall effect is very similar to the integer effect, but it happens at partial filling of a Chern band. It was seen first in the 1980s. There are many different fractional quantum Hall phases. They also have edge states. They also have quantized Hall conductance, but it's quantized to a fractional value. And they're associated with the existence of ground states that are insulating but have elementary excitations of fractional charge and fractional statistics. Okay. More recently, just in the last year, actually, a bunch of experiments have found that you can actually have this by a different mechanism at zero magnetic field. Again, sort of in the same spirit as the quantum anomalous Hall effect. You can have spontaneous magnetization and a sufficiently flat band, and you can also get fractional quantum Hall physics. But this is sort of a somewhat rare, but relatively well understood phenomenon at this point, right? But experimentally, not completely worked out. So there's in particular one beautiful prediction from due to Xiaogan Wen in the early 1990s, which looked at the question of what is the nature of this Luttinger liquid on the edge of a fractional quantum Hall state. Okay, and the basic prediction is that unlike one-dimensional systems, let's say in carbon nanotubes, this chiral Luttinger liquid on the edge of a fractional quantum Hall state has properties that are directly related to the topology of the bulk. So specifically, if you ask what is this Luttinger parameter for a fractional quantum Hall edge state, it's not a function of parameters. It's an absolutely universal, a universal number that just depends on the topology of the bulk. And so the reason why this is a kind of a remarkable prediction, I think, is that you're asking about something that sounds very quantitative. It's not just like how many edge states do I have? It's something about the kind of tunneling density of states of that edge state. It's actually gets a fair amount of, you could imagine that being very detail dependent. But the basic finding is that if you have, let's say nu equals a third, then you expect to have a tunneling power law exponent of exactly 2, 1 over this, 1/3 minus 1, if you're trying to tunnel a whole electron into this chiral edge mode. It's a nice, it's an example of this same bulk boundary correspondence, where something about the topological order in the bulk is reflected in sort of the structure of that edge state. Now, the history of this problem is that, this was predicted in 1990, and immediately experiments were done to try to search for it. Okay, but the technology of the time was that you would take a gallium arsenide heterostructure and try to grow a 3-dimensional electrode on its edge, okay, which was quite difficult to do, right? And it never quite worked. They basically found here, they expected it to be, I think, for the type of experiment they're doing where you have multiple tunneling centers, I think they expect it to be 3, and they found stuff sort of between 2.5 and 2.75. I'm not sure whether they expect it to be 3 or 2, but they got a range. It depended on a bunch of detailed parameters, okay? So they did not find the universal behavior, and the basic explanation for this, there was some back and forth, but I think the basic understanding was this universal regime is guaranteed by the theory, but only at sufficiently low temperatures that all the other physics is irrelevant. So if you have disorder, for example, this might go from being a Kelvin effect to a microkelvin effect, and you're just never going to see it. Okay, and then you're all dominated by the non-universal physics of disorder. Okay, so the opportunity in graphene there's really 2, right? One we've known for a long time, which is that these are systems where if you study the fractional quantum Hall regime, for example, you have a very clean system. You have infinite control, practically speaking, of the carrier density. And so you can study things at very high magnetic fields where energy gaps of these fractional quantum Hall phases are very large. They're, several milli-electron volts. That's actually a very big energy scale for fractional quantum Hall physics. Easy to do experiments in sort of the limit where this is a big energy scale compared to temperature, even disorder, and so on. And we've done this by basically making our entire heterostructure out of graphite and boron nitride, including the gates. Now, this leads to a problem, which is that we'd like to be able to control electric fields on a very fine spatial scale. We'd like to be able to move where the edge states come here and there. And we can't actually do that if you have a single crystal of graphite. So, people tried by not using single crystals of graphite, and I'll sort of leave this literature aside, but they made some progress, but it was always limited by the disorder introduced by just how you fabricate these structures. So the thing that's enabled us to sort of make some progress is kind of a neat trick, which I'll describe, which is that it turns out you can pattern graphite in a kind of a nifty way. So you take an atomic force microscope tip, which is coated in metal, and a damp environment like Santa Barbara, okay? And you bring this tip very close to the graphite, and then you pull it away a little bit, and a little water meniscus forms between the graphite and the metal. And then you put a voltage on that metal tip. And what happens inside this little meniscus, which is about the size of the AFM tip, so maybe 10, 20, 50 nanometers, is that you just electrochemically oxidize the graphite. You just burn it. You just turn it into carbon dioxide and a bit of amorphous carbon. So that's very cool. You can cut right through this graphite, and you can do so on, a few tens of nanometer scale. Okay, so that's cool thing number one, but then there's a real miracle, okay? And the miracle is that if you then try to pick up this cut up piece of graphite with a boron nitride, you pick up only the parts that you wanted, and you don't pick up any of this residual amorphous carbon. So you can now pattern gates with sort of 10, 20, 50 nanometer resolution in whatever shape you want, and then you can integrate them into your heterostructure as you pattern them. So we basically, sort of worked out how to do this and develop this process, and then we can make single controllable point junctions between different fractional quantum Hall states. That's the experiment I'll tell you about in the last, 10 minutes or so. Okay, so the way this device is constructed, you basically have 4 gates. These are going to be the electrostatic gates. You're going to tune the voltages on them to create a constriction between, let's say, this east region and this west region, which are going to host some fractional quantum Hall states. And if you do this, let's say, in integer quantum Hall, you'll find that you can pinch off individual edge modes, and it sort of behaves like a nice quantum point contact, so-called, right? And it doesn't show any signs of, localized states due to disorder. But let me show you the, sort of the experiment that I think is really the most fun one we've done so far, which is to just try to use this to study a single point contact tunneling between an integer quantum Hall state where you have whole electrons and a fractional quantum Hall state, which is a chiral interliquid. Okay, so if you do this, you can study its bias dependence and as a function of like how narrow you make this constriction and how high the barrier is between these two. And what you see is that indeed there's a suppression of the conductance at low tunneling energies. So if you don't give the electrons enough energy, they don't go in. That's what you expect to see for a chiral Luttinger liquid. You can't put electrons into this chiral Luttinger liquid at low energy. Okay, but if you do, but can it be quantitative? Right? There's very quantitative predictions in the universal low temperature, low voltage bias regime. You expect T squared and V squared power laws, and that's it. Right? Nothing else. If you go to low enough energies, that's what you're supposed to see. And if you just do the experiment, no tune-up, it just works perfectly, right? You just get T squared and V squared. It's what you're supposed to do. You go to some different density, some different filling inside the plateau. You get T squared and V squared, and there's just no tuning, within a couple of percent. So things work very nicely. We see this universal regime. But it turns out to be even more interesting problem than that, because you can now try to study, this over a very wide range of parameters. In particular, you can ask, what happens, does everything work quantitatively? If I make the barrier bigger, then this regime should go to lower temperatures. Can you do that? Yes, it all collapses to this beautiful scaling curve, right? But it turns out there's actually sort of two sides to this problem. And actually this problem, because it's one of these quantum impurity problems, so-called, these are all, many of these were solved exactly by, I think this one was solved by like beta ansatz in the early 90s. So you know a lot about this problem theoretically. And in fact, one way to think about this problem is that the universal regime is essentially where the junction between a nu equals a third and nu equals 1 wants to be disconnected, right? That's what this is telling you. Oh, they represent the edge states in this is not going to show up there, but they represent the 1/3 edge state and the nu equals 1 edge state. So one of them has a whole electrons. It's basically a 1D channel carrying whole electrons, and one is a 1D channel carrying fractional quasiparticles. At low biases, you are in this universal regime where you basically have low conductance. But what you can try to do is paste together this nu equals a third edge state with this nu equals 1 edge state by making the barrier between them extremely shallow. Okay, it's still true that at arbitrarily low energies you won't be able to tunnel, but it turns out there is another unstable fixed point in the RG language where it's something else happens. And in particular, there's a really unusual process that dominates this fixed point. So here you're sort of trying to tunnel whole electrons into the 1/3, but if you glue these two together, you might think that the dominant process is that, well, I have to wait for 3 quasi-particles of 1/3 charge to come to the junction, and then they'll turn into a whole electron. One side of these has quantized charge E/3, the other has quantized charge E. Maybe you wait for 3 of them to come and jump across the junction at the same time. That turns out not to be the dominant process. The dominant process is that when you try to inject, is that basically at this fixed point, 2 electrons come in, or 2 quasi-particles come in that have E/3 charge each. 1 electron goes across, sorry for the bad resolution here, and a negatively charged hole is retroreflected into the upstream mode. This is basically analogous to Andrea reflection at a superconductor metal interface, where an electron comes in, a Cooper pair goes out, and a hole is retroreflected. It comes from the fact that you have a boundary between a state where the low energy excitations have one type of charge and the other where they have a different multiple of that charge. Okay, but in the fractional quantum Hall context, you can actually measure the currents and voltages on each of these limbs of this point contact. So for example, just since I'm running out of time, I'll do this kind of quickly. You can inject voltage here, which will inject some current, and you can measure the voltage that's reflected. And you see that if you put a volt here, or more likely a millivolt, you'll get minus half a millivolt on the other limb, which is just coming from the fact that every time you put 2e in here, you get a negative current, okay, in order to get 1 electron across the junction to the other side. Okay, so it's like, what you're seeing is this retroreflected charge. Just to to finish this story, it turns out that there was a very clever idea, again dating, to the 1990s from Bert Halperin and his student at the time, which says that basically one way to think about this junction is it's a perfect current mirror. Okay, every time you put in 2E, you get E out one side and minus E. 3E out the other side and minus E up the other side, right? It turns out if you just wire it up this way, so that you're now injecting voltage from the integer side, I'll leave sort of the details aside, and you work out the physics of this perfect current mirror, you can use a perfect current mirror just as you can in electrical engineering to make a voltage transformer. Okay, but here this perfect current mirror is not powered by some transistors. It just comes from the fact that you've made a junction between a single adiabatic junction between two fractional quantum Hall edge modes. So just to give you the idea, what's happening is you're driving a voltage in, right? It drives some current. There's some current mirroring that happens at this junction, and then there will be some voltage that develops on this output electrode. And if you work it out, you find that it's higher. It's 3/2 higher. Now, if this is a perfect current mirror, then there's no fluctuations. Every time you put in a 2E, you get a minus E coming out the other side. If there's no fluctuations, there's no dissipation. So you can ask, for this voltage transformer, how close is it to this dissipationless limit? So you can measure, for example, the power efficiency. How often is this process happening rather than some other process? And it turns out to be very close to perfect. So you get something like 97% efficiency and a gain of 1.47 rather than 1.5, because essentially every time you try to inject an electron, it splits into two positively charged E/3 quasiparticles and one negatively charged E/3 quasiparticles. It just works very well. In fact, the only reason that it doesn't work perfectly is basically because this is, strictly speaking, not a stable fixed point of the RG. And so, at very low energies, the junction wants to separate itself.